Hi everyone, I'm Geon from KAIST. Today, I'm going to present our work titled Time Plus, Temporal Hypergraph Motifs and Fast Algorithms for Exact Counting. Hypergraphs are everywhere. Hypergraphs consist of nodes and hyperedges, where each hyperedge is a subset of any number of nodes. Groupwise interactions, which are naturally represented by hypergraphs, can be found in many areas in our life. Collaborations of researchers, co-purchases of items, and joint interactions of proteins. In many cases, hypergraphs evolve over time, and in this case, we model the hypergraph as temporal hypergraph, which is a sequence of temporal hyperedges. Note that temporal hyperedges consisting of the same set of nodes can appear at different timestamps. In this work, we propose tools for answering a fundamental question for mining temporal hypergraphs. What are local structural and temporal properties of real-world hypergraphs? In structural aspect, we observe how a sequence of three temporal hyperedges overlap each other. And in temporal aspect, we investigate how temporal hyperedges appear within a short period of time. First, let's review some backgrounds of this work. Hypergraph motifs, or H-motifs, are basic building blocks of static hypergraphs. H-motifs are defined for describing connectivity patterns of three connected hyperedges. The three hyperedges are naturally represented as the Venn diagram with 7 subsets, and the emptiness of these subsets is considered to describe the pattern. While there can exist more than 100 different types of patterns with 7 subsets, H-motifs are defined by 26 different patterns. Let's see an example. Given a hypergraph with 4 hyperedges as in the figure, there exist 3 instances of 3 connected hyperedges. All of them are distinguished by different H-motifs. For example, 3 hyperedges E1, E2, and E3 form an instance of H-motif, and the region 1, 2, 3, 6, and 7 in the Venn diagram is non-empty, which corresponds to the pattern of H-motif 6. Now let's see how we define the new concept, temporal hypergraph motifs. Our question is how to define motifs which describe local structure and temporal patterns of the temporal hypergraph. In this work, we define temporal hypergraph motifs, or TH-motifs in short, that describe both structural and temporal patterns of the sequence of 3 connected temporal hyperedges. Note that each temporal hyperedge is a pair of set of nodes and the timestamp it arrived. First, how can you capture structural properties of hypergraphs? Motivated by the interesting observations using static H-motifs in static hypergraphs, we consider the emptiness of 7 subsets among the 3 hyperedges. Then, how can we capture temporal properties of the hypergraph? We consider 2 aspects. First, the 3 temporal hyperedges should arrive within the predefined time interval delta. Second, the order of the 3 temporal hyperedges are taken into account, so structurally equivalent TH-motifs can be distinguished by at most 6 different patterns. Consider a temporal hypergraph of 8 nodes and 6 temporal hyperedges, and let's assume that delta is 3. A sequence of 3 temporal hyperedges E2, E3, and E4 is an instance of TH-motifs. They are connected and arrived within delta time. On the other hand, a sequence of E1, E3, and E4 is not an instance of TH-motifs, even though they are connected, since they do not arrive within delta time. This means that TH-motifs capture both structurally and temporally local information of the temporal hypergraph. There are 96 TH-motifs, which are distinguished by the emptiness of the 7 subsets and the orders of the temporal hyperedges. Now let's see what we have found using the proposed TH-motifs. Our first observation is that real-world hypergraphs are clearly distinguished from randomized hypergraphs. As seen in the figures, the distributions of the number of instances of each TH-motifs are very different between real-world hypergraphs and randomized hypergraphs. Second, TH-motifs distinguish domains. We computed characteristic profile, or CP, which is the relative significance of each TH-motif of each dataset. Interestingly, the distributions of CPs of datasets from the same domain are very similar, while those from different domains are very different. We compared the distinguishing power with static H-motifs. As shown in the figure, TH-motifs are more powerful in distinguishing datasets based on their domains. TH-motifs can help predict future hyperedges. We trained a logistic regression model using 3 different features to predict whether a given hyperedge is true or fake. THM96 and THM26 are vectors which represent the number of instances of each TH-motifs that a temporal hyperedge is contained in. SHM26 is a vector using static H-motifs. As shown in the figure, using TH-motifs as features gives more accurate prediction, indicating that using temporal information is very helpful when predicting future hyperedges. Now let's move on to the methods to count the instances of TH-motifs. For our naive baseline, we consider a dynamic programming approach. In this method, it reduces the temporal hypergraph to the induced static hypergraph by removing the timestamps and duplicated temporal hyperedges. Then, from the induced static hypergraph, it enumerates all the instances of static H-motifs. From the instances of static H-motifs, it counts the instances of TH-motifs based on the orders of the temporal hyperedges that induces them. Here, it uses dynamic programming to efficiently count the instances. However, the problem of DP is that it enumerates every connected instances in the induced static hypergraph, ignoring any temporal information. Only a small fraction of the instances enumerated in the induced static hypergraph are used to count any instances of TH-motifs. To exploit this finding, we propose THyMe, a preliminary version of counting TH-motifs. THyMe exhaustively enumerates the instances of TH-motifs, so there is no redundant enumeration, which was the problem of DP. It slides a temporal window of size delta and incrementally maintains the projected graph P, whose node is the temporal hyperedge of the temporal hypergraph within the window. Let's consider following example with delta 4. The projected graph P is incrementally maintained with response to the temporal hyperedges that either enter or exit the sliding temporal window. Each new temporal hyperedge is added to the projected graph as a node, and those whose timestamps are at least delta far away from the current timestamp are explored and removed from the graph. Once the projected graph is updated, it enumerates the graph and counts the instances of 3 connected nodes in the graph. However, there are some properties of real-world temporal hypergraphs which can degrade the performance of THyMe. First, duplicated temporal hyperedges are common in real-world temporal hypergraphs. This means that structurally same temporal hyperedges are added as different nodes in the projected graph P, which is inefficient in terms of speed and scalability. Second, future temporal hyperedges are more likely to repeat recent hyperedges. This means that temporal hyperedges in real-world hypergraphs are temporally local, and duplicated temporal hyperedges are likely to co-appear in the temporal window. So, even though the projected graph is incrementally updated based on the sliding temporal window, identical nodes appear within the window. In order to avoid the inefficiency due to the duplicated hyperedges, we propose ThyMe+, an advanced version of counting instances of TH-motifs. ThyMe+ incrementally maintains the projected graph Q, where induced static hyperedge is represented as a node. Each node maintains a set of timestamps of temporal hyperedges inducing a particular static hyperedge. Similar to the projected graph P in time, ThyMe+ incrementally maintains the projected graph Q based on the sliding temporal window. If the structurally same temporal hyperedge arrives within the temporal window, then the projected graph Q does not change. Different from ThyMe+ avoids the exhaustive enumeration of instances of TH-motifs by counting them based on the timestamps of the nodes. We evaluated the speed and efficiency of the proposed methods. ThyMe+ is faster and space efficient than TP and THyMe in all datasets. Now let's wrap up the presentation. In this work, we propose temporal hypergraph motifs for describing structural and temporal patterns of real-world temporal hypergraphs. Code and datasets are available at our GitHub. This is the end of our presentation. Thank you for listening.